Hello students of class 10, this is Advanced Mathematics, page number 105. Okay, you see division algorithm. The students have already required the concept of division along with addition, subtraction and multiplication in arithmetic. Here we shall discuss about some important properties and application associated with the operations of division in integers. The operations of division of an integer by another integer is known as division algorithm. We shall explain the concept of division algorithm with the help of a theorem. This is your theorem 1, division algorithm. For two integers a and b with b greater than 0, there exist unique integers q and r such that a is equals to bq plus r, where a is greater than or equals to 0 and less than b. The students might remember the form of this theorem encountered in their lower classes. It is a relation involving dividend, divisor, quotient and remainder. Dividend is equals to divisor into quotient plus remainder. This relation has been mentioned as the division algorithm in above, where dividend is equals to a, divisor is equals to b, quotient is equals to q and remainder is equals to r. Obviously the remainder is always less than the divisor. To express in simple term, if an integer a is divided by a positive integer b, then we get a total of q parts, each being equal to b, possibly leaving some remainder, possibly leaving some part r less than b. So next it is our proof of division algorithm. So this proof we will not discuss in this video. Okay, this proof we will not discuss it in this video. Okay, we will go to, you see, the applications of division algorithm. Okay, we will go to applications of division algorithm. We will start from example 1. So before we go there, you see, in our lower classes we have already learned this theorem that dividend is equals to divisor into quotient plus remainder, and this is division algorithm we have in class 10 you have already got in the general maths. Okay, the division algorithm you have already got in your general mathematics. So if two integers a and b with b greater than 0, there exist unique integers q and r such that a is equals to bq plus r, where r is greater than or equals to 0 and less than b. Okay, so next it is our some applications of division algorithm. Example 1. So that the square of an integer is expressible in the form 4m or 4m plus 1, where m belongs to z. So now here you see, this is our some application of division algorithm. Okay, some application of division algorithm. The division algorithm, what is the division algorithm? We already know that it is a is equals to bq plus r, where r is greater than or equals to 0 and less than b. This is our division algorithm. Now what are the applications of division algorithm? The applications of division algorithm, you see, first it is example 1. Example 1. Example 1 saying that so that the square of an integer, is expressible. Square of an integer is expressible in the form 4m or 4m plus 1, where m belongs to z. So that the square of an integer is expressible in the form 4m or 4m plus 1, where m belongs to z. Okay, so I will take that, let a be an integer. Okay, let a be an integer. So by division algorithm, A is equals to BQ plus R, where R is greater than is equals to 0 and less than B. Okay, A is equals to BQ plus R. Wait a minute. 1 minute. By division algorithm, A is equals to BQ plus R, and one thing I will write where B is equals to, okay, B is equals to, in here you see it is, I have to express it in the form of 4m and 4m plus 1. So therefore B value I can take 4, okay, B value I can take 4, but B value I will take 2, where B is equals to 2 and R is greater than is equals to 0 and less than B. B value, why I have taken 2 instead of 4, that one I will say why I have taken B value 2. So since R is less than B, R is greater than is equals to 0, okay, and R is less than B, okay, so therefore you see in here I will write, wait a minute, let me write nicely. By division algorithm, A is equals to BQ plus R, where B is equals to 2, okay, B is equals to 2, so B is equals to 2, so 0, R will be greater than is equals to 0 and it will be less than 2, okay, so hence R is equals to 0, 1, R is equals to 0, 1, okay, R value will be 0 and 1, okay. So now for R is equals to 0, okay, for R is equals to 0. So if R value, if I give 0, then this expression it will become A is equals to 3Q. Understand? Because B value, A is equals to 2Q. A is equals to 2Q because B value here it is 2. Okay, so A is equals to 2Q plus R there, but R value is 0, so A is equals to 2Q I will get. Now you see what question it is what saying. I have to show that the square of an integer is expressible in the form 4m or 4m plus 1, where m belongs to z. Okay, so A is equals to square of an integer. Yes, A is an integer. Now square of an integer, so therefore A square I will do. Okay, A square is equals to 2Q the whole square I will get. Okay, A square is equals to 2Q the whole square. So I will get A square is equals to 4Q square. Okay, A square is equals to 4Q square. A square is equals to 4M, where M is equals to Q square. Okay, where M is equals to Q square. Okay, and where M is equals to Q square and M belongs to Z. Okay, and M belongs to Z. So what I did here, you see, I showed that the square of an integer can be expressed in the form of 4m, where m is an integer. Okay, where m is an integer, and m value it is equals to Q square. Okay, now in here, first I check for r is equals to 1. Now I will check for first I check for r is equals to 0. Now I will check for r is equals to 1. So for r is equals to 1, it will become A is equals to 2Q plus 1. A square I will do 2Q plus 1 the whole square is equals to this one, it will become 4q square plus 1 plus 4q. Okay, so this one I can write it as 4q square plus 4q plus 1. From here I will take 4q common. I will get q plus 1 plus 1. Okay, q plus 1. This one I got. So now this thing I can write it as is equals to 4m plus 1, where m is equals to q plus 1 and m belongs to z. Okay, where m belongs to z. So now the last line I can write, thus the square of an integer, last line I can write, thus the square of an integer, thus the square of an integer can be expressible, thus the square of an integer can be expressible in the form in the form 4m or 4m plus 1, where m belongs to z. This sentence at last I can write it down. So in here you see, first of all, example it is saying that show that the square of an integer is expressible in the form of 4m or 4m plus 1, where m belongs to z. So first of all I will take an integer. Let a be an integer. So by division algorithm I will get that a is equals to bq plus r. Okay, a is equals to bq plus r, where b value I will take as 2. B value I can take 4 also, because in here I have to express it in 4m. So b value I can take 4 also. But b value I have not taken 4, because you see, if b value I will take 4, then r value, first of all, r value you see, if b value if I take 4, then r will be greater than is equals to 0 and less than 4. Okay, so r is equals to 0 will come, 1 will come, 2 will come and 3 will come. So after checking for 1, I have to again check for 2, again I have to check for 3 also. Understood? So therefore b value I have taken a lowest multiple of 4. Okay, b value I have taken a lowest multiple of 4, therefore b value 2 I have taken. So first now if b value 2 I take, then r value will be 0 and 1. So therefore for r is equals to 0, a is equals to twice q become. Squaring both sides, a is equal to 4m I will get, where m is equals to q square and m belongs to z. Next again for r is equals to 1, a is equals to 2q plus 1. Squaring both sides, I will get this. Now I will have to see whether this expression I can express it as 4m plus 1 or not. Yes, is equals to 4m plus 1, where m is this whole value. M is equals to q plus 1 and m belongs to z. So therefore what I showed, that a is an integer. The square of an integer can be expressed in the form of 4m and can be expressed in the form of 4m plus 1. Thus the square of an integer can be expressed in the form of 4m or 4m plus 1. This one finished. Okay. So next I will go to example 2. Okay, next I will go to example 2. Next you see, I will go to example 2. So this is example 2 saying that so that the square of an odd integer, the square of an odd integer can be written, the square of an odd integer can be written as 8m plus 1, where m belongs to z. So solution in here, first of all I will take, let a be any integer, then by division algorithm, a is equals to bq plus r, where b is equals to I will take 4. Okay, b is equals to I will take 4. So r will be greater than is equals to 0 and less than 4. Okay, so hence r is equals to 0, 1, 2, 3. Okay, r value will be 0, 1, 2, 3. Okay, so in here I can write that thus a is equals to, for r value 0, okay, for r value 0, a is equals to, I will get 4q plus 1. For r value 1, I will get 4q plus 1, 4q plus 2 and 4q plus 3. Okay, now clearly 4q plus 1 and 4q plus 3 are, these two integers are odd integers. Okay, these two integers are odd integers. Okay, from these four integers, these two are odd integers, and I have to show that the square of an odd integer. Okay, the square of an odd integer. So I will have to show that the square of these two integers, I can write it in the form of 8m. Okay, so therefore a is equals to 4q plus 1. Squaring both sides, I will get 4q plus 1 the whole square. Okay, so this one is equals to, I will get 4q the whole square plus 1 plus 2 into 4q plus 1, which ultimately, let me rub it, this top part, let me rub it. So ultimately I will get here, this is a square is equals to, I will get 16q square plus 8q plus 1 I will get. Okay, so now from here you see, if I take 8q if I take common, then I will get 2q plus 1 plus 1. So this one I can write as 8m plus 1. Okay, 8m plus 1. Where m is equals to q 2q plus 1. Okay, m is equals to q 2q plus 1. M belongs to z. Okay, so therefore I show that the square of an odd integer, can be expressed in the form of 8m plus 1. Okay, and next, for similarly a is equals to 4q plus 3. Okay, similarly a is equals to 4q plus 3. Again, squaring both sides, I will get a square is equals to 4q plus 3 the whole square is equals to 4q the whole square plus 3 square plus 2 into 4q into 3. This is 16q square plus 9 plus 4 2s are 8, 8 3s are 24q. So this is equals to 16q square plus 24q plus 9. Okay, so now you see, I can take 8q, wait 1 minute, this is 16q square plus 24q, 9 I can write as 8 plus 1. So from these three terms I can take 8 common, so I will get 2q square plus 3q plus 1 is equals to 8m plus 1, where m is equals to 2q square plus 3q plus 1. Okay, m is equals to 2q, so this one, okay, in here I will write this one, m is equals to q 2q plus 1 belongs to z. Okay, belongs to z for q belongs to z. Okay, for q belongs to z, m is equal this thing belongs to z for q belongs to z. Okay, Again this thing m is equals to this one, it belongs to z, that means that only m belongs to z for q belongs to z. Okay, for q belongs to z. So last line I can write, thus the square of any odd integer is expressible in the form of 8m, expressible in the form of 8m plus 1, where m belongs to z. Okay. So now next I will go to example 3. Example 3. For any integer a greater than is equals to 1, so that a square plus 2 by 3 is always an integer. Okay, for any integer a greater than 1, so that a square plus 2 by 3 is always an integer. So in here, by division algorithm, a is equals to, by division algorithm I get that this is a is equals to bq plus r, where b is equals to, I will get 3. Okay, so therefore the values of r will be greater than is equals to 0 and less than 3. Hence r is equals to 0, 1, 2. Okay, r is equals to 0, 1, 2. For r is equals to 0, okay, for r is equals to 0, it becomes a is equals to 3q. Okay, a is equals to 3q. Now this 3q, okay, this 3q value I will put it in here. Okay, so this one you see, a square plus 2 by 3, this things becomes 3q the whole square plus 2 by 3. So this one is equals to, it becomes q 9q square plus 2. Okay, 9q square plus 2, and this will be an integer. Okay, so therefore this one I can write as belongs to z. Okay, this one I can say that belongs to z since q belongs to z. Okay, since q belongs to z, q is an integer, so therefore this is q 9q square plus 2, it will belongs to z. Okay, next again, for a is equals to for r is equals to 1, okay, for r is equals to 1, we will get a is equals to 3q plus 1. For r is equals to 1, we will get a is equals to 3q plus 1. Now again, this one a square plus 2 by 3, a value I have got 3q plus 1, so this is 3q plus 1, 3q plus 1 the whole square plus 2 by 3 I will get. Okay, by 3 I will get. So now you see this one I will have to break it into formula. This one I will have to break it into formula. So this is 3q plus 1. This one let me break it into formula. It will become 3q the whole square plus 1 square plus 2 into 3q into 1 plus 2 by 3 I will get. So this is 3q plus 1. This is 9q square plus 1 plus 6q plus 2 I will get by 3. So this is 3q plus 1. This will be 9q square. Okay, this will be 9q square plus 6q plus 3 by 3 I will get. So now from here if I take 3 common, 3q plus 1, this will be 3q square plus 2q plus 1 by 3 cut, ultimately I will get 3q plus 1, 3q square plus 2q plus 1, and this one I can say that this belongs to Z since q belongs to Z. Okay, this one I can say that this thing belongs to Z since q belongs to Z. Okay, next again for r is equals to 2. Okay, for r is equals to 2, a is equals to 3q plus 2 become. Now again I will have to put this value. So therefore you see a square plus 2 by 3. Again I will have to put the value of a here. 3q plus 2, and this is 3q plus 2 the whole square plus 2 by 3. This one let me solve it. So this is equals to, you see, 3q plus 2, 3q the whole square plus 2 square, 2 into 3q into 2, and this one 3q plus 2 by 3 I will get. So this is 3q plus 2, 9q square plus 4 plus 12q plus 2 by 3. 3q plus 2, 9q square plus 12q plus 6 by 3. So this is equal to 3q plus 2. From here I will take 3 common. From here I will take 3 common. So therefore I will get here 3q square plus 4q plus 2 by 3. So now you see 3 cut, 3q plus 2, 3q square plus 4q plus 2, and this will belongs to Z. Okay, this will belongs to Z since q belongs to Z. Okay, so therefore I can say that last line, therefore for any integer a, okay, so therefore for any integer a, this one a square plus 2 by 3, okay, is an integer. Okay, therefore I showed that for any integer a square plus 2 by 3 is an integer. Next you see example 4. Next you see example 4 here. This is your example 4. So that the square of an even integer, so that the square of an even integer is even, and the square of an odd integer is odd. Okay, I have to show that the square of an even integer is even and the square of an odd integer is odd. So now you see let a be an even integer. Let a be an even integer. So therefore a is equals to, I can write it as a is equals to twice q. Okay, for q belongs to z. Now a square, it will be 2q the whole square. This will be is equals to 4q square. Okay, so this one I can write it as 2 into 2q square, okay, is equals to twice m, where m is equals to 2q square belongs to z. Okay, so therefore a square is equals to twice m I got. So therefore I can say that a square is an even integer. Okay, therefore I can say that a square is an even integer. Okay, next again I will take, again let a be an odd integer. Okay, let a be an odd integer. So I know how odd integers looks like. A is equals to 2q plus 1 for q belongs to z. Okay, okay, since a is an odd integer, so therefore I have taken a is equals to 2q plus 1 for q belongs to z. Now I will do square. Okay, so a square is equals to 2q plus 1 the whole square, which will give me 4q square plus 4q plus 1 I will get. Okay, so this one you see square, I have to show that the square of an even integer is even and the square of an odd integer is odd. Okay, so from here now I can take 2 common. Okay, I can take 2 common from this. So this one I will get 2q square plus 2q I will get plus 1. So this one 2m plus 1, where m is equals to 2q square plus 2q. Okay, m is equals to 2q square plus 2q, and m belongs to z. This belongs to z. So therefore a square is an odd integer. Okay, a square is an odd integer. That one only I showed, that if I take that a is equals to, okay, first of all I took that let a be an even integer. So since a is an even integer, so I can write it as a is equal to twice q for q belongs to z. Okay, so a square is equals to, I have to show that the square of an even integer, the square of an a here is an even integer, so I have to show that a square is also even integer. So therefore a square is equal to 2q the whole square I will get is equal to 4q square. Now this one I can write it as 2 into 2q square. So this one I can consider it as m. Okay, so this thing becomes twice m. A square became twice m, where m is equals to 2q square belongs to z. So therefore a square is an even integer. Yes, a square is equal to twice m I got. So therefore I can say that a square is an even integer. Net again let a be an odd integer. So since a is an odd integer, so therefore a is equals to 2q plus 1. A square, it will become this one. I can take 2 common from these two. I will get 2 bracket start 2q square plus 2q plus 1. This one I can take it as m. So 2m plus 1, where m is equals to 2q square plus 2q belongs to z. Therefore you see a square is equals to, I got 2m plus 1. Yes, 2m plus 1. It is an odd integer. So therefore a square is an odd integer. That only I showed. If the integer is even, then its square will be also even, and if the integer is odd, then its square will be also odd.